Good afternoon. We'll just start in a couple of minutes. We are waiting for few attendees to join, and then we'll start in a couple of minutes. Marco, we will start.
Okay.
Yeah. Good afternoon. I, Suruchi Shanbhag, on behalf of Shachi Engineering Private Limited and Klaren International, welcome you all to this webinar. Thank you for taking the time for this important topic, MVR and self-cleaning evaporators. This game-changing technology is transforming the industry in India and around the world. I also thank Marco, Chief Technical Officer of Klaren International Netherlands, who will share insights on the technology and its application today. So the format is somewhat like this. I'll share a brief about Shachi Engineering in first 10 minutes, and then Mr. Marco takes over to take a deep dive into the self-cleaning evaporator technology. As a core team member in development of this technology, Mr. Marco has many valuable insights to share, both from business and practical points of view. Towards the end, we could take some questions that you may have for about 10 to 15 minutes. Shachi Engineering and Klaren International have been in collaboration for the past 5 years. It has been a relationship driven by common value system, commitment, and performance standards that we have jointly set in the Indian market. Shachi Engineering is serving a vast range of application. Marco, can you go to next slide?
Yeah.
From the competitive and high volume dyes to highly premium and sensitive flavors and fragrances. As Shachi Engineering, we have been successfully serving the two extremes of the market and everything in between. The common thread joining these two extremes is quality. At Shachi Engineering, we have a strong bias to quality. In many ways, we believe that reducing cost is important, but the best strategy to reduce cost is to choose quality. Fortunately, over the last 20 years, we have been able to work with quite a few like-minded clients who believe in the same thought process. The partnership with Klaren International has the same thought at its foundation. We have served 350 plus projects across the different categories over the last 2 decades, from some of the largest process industry to the most specialized one or Indian companies or MNC plants. We have worked with all kinds of companies that believe in the quality and put it first in priority. One of our key differentiators in the R&D is the R&D capability. In fact, the partnership with Klaren International is a result of this constant quest to do something new, to improve upon what's already there. It shows in our comprehensive approach in R&D, maybe product price, equipment life cycle, or end users need. We love accepting new challenges and reaching new horizons. The implementation of self-cleaning evaporation technology is one such example for the recent times. Quality. As I've mentioned in the previous slide, is our core why. The quality perspective or bias is evident in our capability standards. We follow a technology partnership. A key insight that we derived recently is that over 60% of our plants are being used for export-centric product. Our designs and solutions are driven by quality at its core. We share the quality vibe with Klaren International's team as well. If we were to express Shachi Engineering in one slide, the elevator pitch, and in one word, it would be expertise. We recently completed 22 years in the business. It has been a very fulfilling journey, and now with tie-ups such as the one with Klaren International, we are really trying to bring and adopt the most innovative global technology for Indian needs. This again is an expertise and innovation in itself, as you will see in the examples of installations that Marco will speak about in the slides ahead. The one thing that we have been focused on right from the beginning is the future. We are always thinking of the future. What would it look like? And constantly adapting our practices to meet the needs and expectations of the future. Whether being the innovative self-cleaning evaporator technology to Indian market recently, the vision for the future is embedded deeply in everything we do. And a very important part of this future is our collaboration with Klaren International, Netherlands. We have joined hands to change and transform the market standard for evaporator in specific applications. Our goal is to change the results and performance matrices of evaporators in our chosen niche. We are here to create the future of evaporators with self-cleaning technology. I thank all the esteemed audience today for taking out the time to attend the webinar. We look forward to connecting with you and take this ahead in the near future. It is my pleasure to introduce our expert speaker today, Mr. Marco from Klaren International, Netherlands. As Chief Technical Officer, Marco is responsible for technology development of self-cleaning heat exchanger technology. He has been the force and guidance for driving the implementation of this innovative technology in India with Shachi Engineering. I am happy that today the installations in India stand as a proof of the benefit of the self-cleaning technology globally. I now request Mr. Marco to walk us through this game-changing and revolutionary concept, technology, and applications. Over to you, Marco.
Thank you, Suruchi. Yeah, from here on, I will take over this presentation, this webinar, and I want to thank Shachi and the team at Shachi for organizing this webinar. And in fact, it's already the third webinar that we are giving about the self-cleaning technology and the introduction in India. And today the focus will of course, I will say some words about the self-cleaning technology, but the focus will also be on how to integrate the self-cleaning technology into the Mvr concept, and also to understand what is important when designing and selecting an Mvr. Because what we see in the business is that, yeah, many things are offered, but we really question if some of the systems can work based on how they are designed. So I will explain more about that in the coming webinar. We started to work with Shachi Engineering in India about 3 years ago, and since then we have experienced that it's a fruitful experience, and an experience where quality and performance is really a core value. We are not in the business to only supply a plant and then walk away. No, at the end the customer should be happy and should be happy with the performance. Yeah, a slide I normally start with that in fact shows what problem that we try to solve. So what we see in the treatment of wastewater is that many plants experience severe problems with fouling, or also sometimes called clogging or plugging. In fact, the fouling initially first reduces the heat transfer, and by reducing the heat transfer, of course, the evaporation capacity of the plant is affected. But at the end, complete tubes could be plugged, even limiting the flow, and even furthermore limiting the capacity. And you see some real nasty pictures of a fouling case on the left side. Of course, if you have these types of fouling in your heat exchanger, this will affect the performance. And what I already said, it will lead to reduced capacity. But at the end, already in the design, it will also lead to oversizing, because in the design you need to take into account, in fact, the fouling layer and the effect on heat transfer. So that will result in additional heat transfer area. At the end, if fouling becomes too severe, it will also lead to production losses, downtime, and of course, at the end, you also need to clean it. And cleaning sometimes can really be a tedious task. We recently experienced in one of the units that we were going to revamp that cleaning a 31 tube unit took almost 4 days with water jet cleaning. So that's a really incredible task. I will now show you a short video that we made together with Shachi on the introduction of our technology. I hope it works. Okay, there's an error with the video, so yeah, I will move on then. So what is our technology about? Our technology is to solve the fouling as is occurring in those evaporators. And the way we do this is by introducing cleaning particles to the liquid. So in an evaporator, and especially a forced circulation evaporator, you have a calandria, and from the calandria, the liquid will go to the vapor liquid separator, and then back to the recirculation pump, and then back to the heat exchanger again. So it's a circulating loop. But to this loop, we add a loop with cleaning particles, and the cleaning particles we supply from this downcomer into the inlet channel, and into the inlet channel, the particles are distributed over all the tubes in the heat exchanger. And in fact, one of the core things of know-how that we have is how to design this element such that all tubes will experience the same amount of particles, because that is of course crucial in making sure that all the tubes are cleaned. And that might be simple for a heat exchanger that has 3 or 5 tubes, but it's a lot more difficult if you have a heat exchanger with over 400 tubes. So these particles are taken with the flow upwards through the heat exchanger tubes. And if you would zoom into such a tube, then you would see those particles moving in a chaotic manner. And in this chaotic manner, they would impact each other, but they also would impact the tube wall. And by these small impacts of the cleaning particles with the tube wall, let's say we create a scoring action on the wall, which removes a layer that wants to develop. but it's a light scoring action, so it will not erode the tube walls. It's a light scoring action that keeps the tube wall clean and effectively make sure that a layer cannot develop, because the cleaning mechanism is not so aggressive that it could really clean a tube that already has a thick layer. No, we need it from the beginning. We also need it from the beginning because our system is an integral part of the heat exchanger design. In our system, we use tube velocities which are lower than normal. If you would take a nowadays well-designed shell and tube heat exchanger, it would run with tube velocities over 2 meters per second. And we even now sometimes see always close to 3 meters per second or over. But we run with lower velocities. But to have the same heat transfer coefficient with these low use of the benefit of the cleaning particles, because the cleaning particles increase heat transfer. They increase heat transfer with a factor of 3 to 4 if you would compare it with the same velocities. If you compare conventional design heat exchanger in clean conditions with our system, the heat transfer would be comparable. Of course, with the main benefit that because of the cleaning, our heat transfer coefficient remains the same. After that, the cleaning particles have been transported from the heat exchanger. We separate them again, or not again, but we separate them in a particle separator. And these particles are redistributed or recirculated back to the inlet. And then the liquid will go, in the case of a forced circulation evaporator, to the vapor liquid separator. But in another process, it can also go to a distillation column, or it can go to whatever is the next step in the process. So to summarize, our particles, they clean the tube. At the same time, they increase heat transfer such that we can have a very good heat transfer coefficient. A third effect would be shear tinning, but that's less relevant for wastewater systems. I get a comment that my voice is losing in the middle. Maybe someone can give a question to say if I'm audible or not. Okay, I will continue for the moment. I see my mic is giving a signal. So so these cleaning particles, they flow through the tubes, and by this motion they give this scoring action and clean the tubes. And it's a continuous system. So to give you an example of how this system looks like in real life, because in 2018 we installed not our first system, but the first system in India. We did this project together with Shachi, so we installed it in 2018. This installation was for a multi-effect evaporator plant for wastewater treatment. In fact, the wastewater came from a dye manufacturer in Gujarat. And in this plant, the evaporator was cleaned every 2 weeks. Meaning that every 2 weeks they had to open the calendias, take the water jet machine and clean the tubes, and this could easily take 4 to 5 days. If you look at the fouling issue itself, the fouling was the result of a crystallizing mechanism with calcium sulfate in combination with other salts. It was more complex, but also in combinations with large quantities of organics, COD. And their experience was that they had a very, very thick and hard layer of scale that was very difficult to remove. When we came into contact with this client, we discussed the possibilities to improve this plant, and we had a look at how we could integrate our technology into the first effect of this plant. What we then always do is that we will make a technical feasibility study to see if we really can do the revamp. Because a revamp, of course, you want to try and use existing equipment, and you but you also want that the performance after is better, or at least just as good as what it was before in the clean conditions. So we make this technical feasibility study, and we found out that it was possible to integrate it. And in this case, we were also a bit lucky because it was a 3-pass heat exchanger. And since that, we reduced the tube velocities and would like to be have a comparable flow. But if you reduce the tube velocity and you want the same flow, you need more tubes. But since it was a 3-pass, we could convert the 3-pass into a single pass. And by doing that, yeah, you would need 3 times the number of tubes to have the same flow. But of course, going from 3-pass to single pass, in fact, you get that. So that was a nice coincidence, which resulted that, yeah, it was in terms of the process conditions an easy revamp. In terms of mechanical layout, and because that's the second thing we have to look at, is there space to integrate our components? We also found the possibilities to do this. Because at the end, and you can see that on the right picture, maybe I can show it with the spotlight. On the right picture, you see how the situation looks after the revamp. So we have installed as an additional part the particle separator in between the calandria and the vapor liquid separator. And by this downcomer, we recirculate the particles. And here you see the recirculation to the pump. So also from the mechanical layout, it was possible. And at the end, we have installed this system in 2018. And currently we have over 7,000 hours, and the plant has not been cleaned anymore. I have to now, maybe one moment. So what is of course important then is what was the performance after this revamp, and you can see this. You can see that in this picture, in this figure, where we show the evaporation capacity on the y-axis versus time, and it's shown for the first 900 hours. We now have experience also for a longer period, and what you see is that normally in the blue triangles, you see that within 300 hours the evaporation capacity went from 4 cube per hour to below 2 cube per hour, which was initially what I was talking about, how fouling affects the performance. After the conversion, and you see that in the red triangles, you see that the evaporation capacity remained constant. And in fact, it was a bit of a surprise, not because we were, let's say, doubting our technology in the first effect, but it's a multi-effect where they also had fouling in the second and the third stage. But with our technology, this fouling had reduced. The exact reasons is a bit hard to clarify, but at the end, yeah, of course, this performance was really good, and the major issue fouling in the first effect was solved. In the years after, we also had some regular inspection just to follow our technology, because the client also wanted to validate it as a decision to equip more plants with our technology, which in fact we have done. So on the right, you see a picture taken from one of the inspections, where in fact you can see that the tube has remained clean. Yeah, so and of course that's the proof of the pudding, and that's what we were very happy with, as well as the customer. So what I've just shown you, and the picture here, is the decrease in evaporation capacity versus a constant capacity. And in fact, that is the core of the business case. Because if you would look at a schematic picture, and you can see that on the left, you would see that evaporation capacity goes down from 100% to 50%, and in this typical example, in 28 days, not to exaggerate it. After that, you would stop the plant, clean it, and when it's clean again, it would go back to 100% if you're lucky. In most cases, it will be less because there will be some fouling left, and the cycle will repeat itself. If you would then do the simple math, you would see that the average capacity of this plant is only 60% of the design. And this is, of course, yeah, this is not what customers have paid for. When you buy a plant for 20 KLPD or 50 KLPD, then you want also that it runs, that it treats 50 KLPD and not 25. So what is the real business case, but sometimes it's difficult to put that also in numbers, is that evaporation capacity remains constant. And what we also see is that also for customers in India, this becomes more and more important because legislation is getting more and more tight. And that means that people really, let's say, need the capacity to always treat their wastewater. So self-cleaning and evaporation. Well, there are different ways in which you can use evaporation or convert evaporation into the design of an evaporator plant. You could go for the route of a multi-effect evaporator, or you could take the route of an Mvr unit. And already upfront, depending on the customer situation, there are reasons to go for the ME route, and there can be reasons to go for the Mvr route. In both cases, we can integrate our technology. Today, I will focus a bit more on the Mvr. But some words first about the ME. With a multi-effect evaporator plant, there are multi-effects. So there's always also the question that we have when designing such a new plant or thinking about revamp is which effects to equip with self-cleaning. And we know that our system will need some investment. And at the end, then it's the evaluation, where to put this investment. And what we see is that, and normally then it will be limited to choosing one of the effects. And then you can go two routes. And the first route is that you say, I select the first effect with higher temperatures and lower concentrations, if it is a forward feed plant, or you can choose the last effect with the higher concentrations. When going to backward feed, you could also combine it and say, I choose the effect with the highest temperatures and the highest concentrations. But when looking at Mvr, well, one discussion is solved, and that discussion is that one discussion is solved, and that discussion is about which effect, because in an Mvr there is only one effect. And how does an Mvr work? Well, in fact, the reason why you need much energy for evaporation is that you need to convert water from the liquid phase to the vapor phase. And then you, let's say, need to add the latent heat. But at the moment that you can recover this latent heat, of course you benefit. That's why you have multi-effects. You use the vapor multiple times. But with a multi-effect, still at the end, some part of the vapor is going to the condenser. With an Mvr, all the vapor that you generate is condensed again. So this total heat content is recovered. And that's why an Mvr, let's say in the core of the physics, is a better concept. But how do you get this system to work? Well, that is done by using a compressor. So by a compressor, you upgrade the vapor. You upgrade the vapor in terms of, because that's what you're looking for. You want temperature, because with temperature, you can create the driving force to run the heat exchanger in the system. But you create this temperature by increasing the pressure. So the compressor increases the pressure and then implicitly also increases the temperature, which gives the driving force. I'll just take my spotlight again, which creates the driving force to run this heat exchanger. So the vapor is condensed. In fact, this is also a condenser. And by this condensation, this liquid is heated, it flashes, goes back to the recirculation pump, and then is heated again. And this continues. So you condense the vapor that is generated, and this is fully condensed. So there's no vapor left anymore. Yeah, so that also means that there is no condenser needed anymore. So no cooling tower also to create cooling water for the condenser. So in that sense, a lot of the elements are no longer required that you would require in a multi-effect evaporator. So this is in fact the principle behind the Mvr unit. But now I realize that I forgot one thing, which is very crucial, but I will explain that later, is that the feed. Suppose you have feed in a feed tank with 30 degrees. And this system runs at 85 degrees. So partial vacuum, condensation at 100 degrees. Then, of course, if you add this 30 degrees to this, then you lose a lot of heat to heat the feed back up to the system temperature. So what you need to do is always have a loop with a preheater in which you use the heat that is available in the condensate to preheat the incoming feed such that that is close to your system temperature. And I will say something about that later in more detail, but preferably it should be higher than the system temperature, but definitely not lower. Take one sip of water, one moment. So looking what I already was talking about, the energy part of an Mvr unit. So a multi-effect evaporator with TVR would require steam, of course, but would also require energy, electrical energy to drive the recirculation pumps. And since it's a multi-effect, there will be multiple recirculation pumps which all require their energy. So just comparing two let's say typical systems, you could find that for the multi-effect evaporator with TVR, you need almost 0.3 kg of steam per kg of evaporation, plus the electricity. If you would do the same principle design of an Mvr unit, you would find that you need electricity, which is higher than the ME, to drive the recirculation pump, but also to drive the compressor. So that would be almost double of the ME, but of course there is no steam. If we then convert both the steam inputs or both the energy inputs, steam or electricity, to coal with some simple calculations, assuming an electrical power plant efficiency and an efficiency of a boiler, and a design with a two-stage compressor that has a certain delta T, you could back calculate how much coal, how much primary energy do I need to convert to evaporate 1 cube of water. And then you would find that for the Mvr you need around 40 kg, where for the multi-effect evaporator you would need over 70 kg. So you can, let's say in terms of primary energy, you can, let's say, save a lot of energy by using the Mvr concept. Of course, I realized in some cases, and that depends on steam price, electricity price, it is more beneficial to take a multi-effect evaporator, or maybe there is waste steam available. But if that's not the case, then let's say an Mvr has the benefit of a better energy efficiency. So that is interesting. On the other hand, an Mvr also I would say requires care. And we know that in the market, there are quite some Mvr units that have trouble, and some of them are even not even used anymore. They have, let's say, removed the compressor, or not removed it, but just bypassed it, and they run it on fresh steam, maybe in combination with a TVR. Because some clients experience problems with these Mvr units, and I want to tell a bit more about that today, so that you can understand where this can come from. I'm not saying it comes from this, but it gives you some background. Also, with illustrating some of these elements, I want to, let's say, maybe give you some hints in if you select an Mvr between multiple vendors, and in fact I don't care who it is, of course it could also be Shachi with self-cleaning, but in fact just open and transparent. Please make sure that you know what you're buying and that you have specified what you're looking for. I will tell you exactly what we mean with this. I also see a question coming in. I will later answer those questions in detail, because this question is about startup, and which is relevant, but I come to that later. So three key elements that I want to discuss today is rotating equipment. Why? Well, rotating equipment requires care. And if, let's say, you take care, it's no problem to use it. But if you take too less care, you really could end into trouble, especially with the centrifugal part, but I will illustrate that later. The second point is that in the design of an MVR, you can make choices. And in fact, the choices are a bit between investing upfront, that's more heat transfer area, but that would allow you to run at a lower compressor ratio. Or you can choose to say, I accept a bit higher OPEX, so I run at a bit higher compressor ratio, but then I need less heat transfer area. I have a more compact unit. But they go hand in hand. I will explain. The third point is that the MVR requires a positive energy balance. I will go in detail later, but if this positive energy balance is not there because of too much heat loss or a preheater that is not working, at the end you will lose energy in the cycle and the system will collapse. But more details later. The first point, MVR and rotating equipment. In principle, what we see and what we would also use in our MVR units that we would design together with Shachi is that you can make two choices. You can go for a roots blower or you can go for a centrifugal compressor. You see some pictures here on the slide. In fact, they are taken from the web. I do not have any preference for a supplier at this moment in time. So I just mentioned the name, not because we work with them, but because I find it important that you know what picture I've taken. So let's start with the roots blower. So the roots blower is in fact quite a simple apparatus in which you see two rotors that have, let's say, a certain kind of shape, which makes them what you also can say a kind of positive cavity pump, but then for vapor. So in fact, by just moving the rotors, you move certain volumes of vapor, which you can see a bit in the schematic picture. And by this movement and limiting the leak flow, in fact, you create the compression. This roots blower is able to handle a bit wider range of compressor ratios, because in fact the compressor ratio more comes from the systems before and behind than it comes from the compressor itself. But based on tight clearances, there's less leak flow, so it can handle higher compressor ratios compared to the centrifugal one. A roots blower just has normal roller bearings, so is in that sense also a bit more easy. But there are also some disadvantages, like for example, and the noise it makes. If you have ever heard a roots blower run, well, in my previous company we sometimes tested one, but we always did that after office hours because everyone would really, let's say it, hear a lot of noise. So that's the roots blower. Typically, we would use a roots blower for smaller capacities. If you go to higher capacities, then the best option would be to look at a centrifugal compressor. And in the bottom picture, you see that this directly also shows like a more sophisticated piece of equipment. And in fact, it is. It will no longer have roller bearings, but it will have sliding bearings. And that also means that you need loop oil and that you need a proper lubrication system to make sure that the shaft is supported well. And even in case of a power failure, you need to have backup systems to make sure that the shaft remains rotating and lifted in its bearings. Otherwise, it could sink through these white metal bearings and lead to a lot of damage. So a centrifugal compressor is more delicate. You need to let's say, witness the bearings. You need to witness the vibrations of the shaft, and you need to really take care of this. So that means that, and you also see that it's a larger piece of equipment. It will be for a bigger plant, and that also means that there will also be more plant people available to witness this. One thing which I forget to mention is that in both systems you would need injection water to desuperheat the vapor. So at the end, the vapor coming out of the Mvr compressor is superheated, and you would want to let's lower the temperature. And in the case of the roots blower, you also need to cool the block. So the housing will get heated up by the inefficiency of the blower, and you need to cool this by injecting more water than you would normally expect for de-superheating. But I'll show you later, that will also give you an advantage. So this is the first key element, is we talk about rotating equipment and we need to take care of this. The second key element starts with saying something about boiling point elevation and how this reflects to the design, I will say later. But to start with, what is boiling point elevation? If we have a wastewater, if we have an effluent that contains salts, dissolved salts, then these dissolved salts influence the boiling point. And that means that effectively your liquid will boil at a higher temperature than what you would expect with the pressure. So for example, let's just take atmospheric conditions of boiling. Normally the water would boil at 100 degrees, but with boiling point elevation, it could boil at 103, 104, 106 degrees. So typically, for concentrated effluents, this boiling point elevation will be between 2 and 7 degrees. Boiling point elevation you can calculate based on the composition of your effluent, but be careful, you need to calculate it for the concentrated. You need to calculate it for the concentrated liquid, which will run in your evaporator. So there are methods available also within Shachi to calculate this boiling point elevation. And if you, let's say, don't trust or you're not absolutely sure about your composition, another way is just doing the concentration in a lab and just measuring the moment it starts to boil. In the bottom pictures, you see two different salts, sodium sulfate and calcium chloride. And you can see that for calcium chloride, for high concentration, this boiling point elevation really can become substantial. And that means that it's really important to consider this, because I will show you that in the next slides. In the design, boiling point elevation will affect your heat exchanger design. And this is really something to carefully consider. Yeah, for this I need some equations, so allow me in this webinar to go a bit more deep. If you look at the capacity of the heat exchanger, capacity of the Mvr unit, you talk about the heat duty. And the heat duty is the heat transfer coefficient times the heat transfer area times the difference in temperature between the shell and the tube. The duty also is related to the evaporation capacity. And so if the evaporation capacity is, for example, 20 kPd, you can calculate how much kg per second that is, and you can derive how much heat duty does the heat exchanger need to pass. So that is one. If you then zoom into this equation, the tube temperature, in fact, will be the temperature in the vapor liquid separator combined to the pressure in the vapor liquid separator plus the boiling point elevation. So take 100 degree as just atmospheric evaporation, boiling point elevation of 4, then the tube temperature, the inlet, would be 104. If we then look at the other side, the shell side, then the shell side temperature will be dependent on the temperature rise that the compressor gives. And the temperature rise that the compressor gives is linked to the compressor ratio. It's also one of the questions asked. So the compressor ratio is really important because it will define the pressure rise over the compressor, the temperature rise over the compressor. So if you write that, then the difference between shell and VLS is in fact the delta T over the compressor. This is linked to the compressor ratio. So if we combine that, then the heat transfer area that I need will be the heat duty, but that's simply the capacity of the system, divided by the heat transfer coefficient, and divided by the difference between the temperature rise of the compressor minus the boiling point elevation. So already to give you one idea, suppose that my delta T over the compressor is 6 degrees and my boiling point elevation is 6 degrees, there is no driving force for the heat exchanger and the system cannot work. So this is already how important this is. So just to give you examples, a roots blower can have a compressor ratio between 1.4 and 1.9. Maybe it can also go a bit higher, but then let's say the internal leakages, internal inefficiency starts to really become too high, which would mean that the delta T that you can accomplish is between 7 and 16 degrees. If you look at centrifugal compressors, this compressor ratio is more limited for a single stage. And that has to do with just how do you say that, the performance of such a single blade system. And typically, this would have a compressor ratio of between 1.3 and 1.4 for a single stage. So that means if you're offered an Mvr unit with a single stage compressor, you know that the delta T is limited to 7 degrees. But that also means that if your boiling point elevation is 5 degrees, there's not much temperature difference left to drive your heat exchanger. So what you see is that in systems that have effluents, concentrated effluents with high boiling point elevation, you're almost forced to go to a double stage. But you can also imagine, if you take into account the previous pictures, that a double stage compressor is quite an investment, and also it's a lot of machinery. So that's also from that perspective important. But with a double stage, you could go to higher compressor ratios, and of course you have more driving force for the heat exchanger. And that's what I show you in the next slide, is how this affects really the design of your heat exchanger. So in this slide, you see some data for a typical case, and I've calculated based on a conventional heat exchanger. We can also do the same for an heat exchanger with self-cleaning, and that will also be later in the Mvr Calculator that we will supply via our website. But in this case, I just take a conventional heat exchanger, and a heat transfer coefficient of around close to 1000 watt per square meter Kelvin, or 830 kilocalorie per hour per square meter Kelvin. So it's a typical case, and you can change the numbers, but it's important to understand the effect. And you can see the effect in the values between brackets for the heat transfer area. So let's start with case A. In case A, I have a boiling point elevation of 3 degrees. I take a compressor ratio of 1.7. So that would mean that the temperature increase over the blower is around 13 degrees. So you can also, let's say, do that math, but if you lower 13 with 3, you get 10 degrees driving force. There is, of course, it will be a bit lower because there is a temperature rise over the tube as well, but okay, let's take roughly closer to 10 degrees. And with this 10 degrees temperature difference, your heat transfer area, the minimum that you require, would be around 59 square meters. But now we take the same case, and we know that the boiling point elevation is not 3 degrees, but 6 degrees. Then you see that this directly affects the heat transfer area that I require, because then it will be 84 square meters. So my real important message is that if you're a customer that wants to buy an Mvr unit, please specify to all your vendors which boiling point elevation to use, because this will affect the design that they will give you. And at the end, if they assume it, they will take a low one, because then they need to provide less area. But at the end, your system could not work. So you see this effect between case A and B. But if I take a higher compressor ratio, it will take me more energy to drive the compressor. So what can we do? Can we go to a lower compressor ratio? We can save energy. Well, then you see what happens. If you compare then in case C, a boiling point elevation of again 3 degrees, compressor ratio 1.4, the area would be 128 square meters. So that's almost double, or it's more than double, of case A. If you look at case C, you see that the boiling point elevation really gets close to the temperature rise. And then your LMTD reduces so much that your heat transfer area explodes. And so you are over 700% of the initial design. So that means that the heat transfer area is really dependent on these combination between boiling point elevation and compressor ratio. As I said, of course, compressor ratio is linked to energy use. So we go to the right bottom table. In case A and B, I have a compressor ratio of 1.7. And that means that the energy that I need to drive my compressor is around 42 kilowatts. If I go to a compressor ratio of 1.4, this compressor energy has reduced to 26 kilowatts. So that's of course beneficial, because the less kilowatts that you need means that you need less electricity, and that's less money that you spend on electricity. So in fact, what you see is that you need in the design to make a decision between investing in heat transfer area, maybe then lowering the compressor ratio that you need to run at, or going to, let's say, have a lower investment, but that means more operational cost because you need to run with a higher compressor ratio. So this is really an evaluation that you need to make between those two elements. At the end, you could also specify that to vendors to say, let's say that I want to focus on minimizing my operational cost, but then I need a large heat exchanger, larger heat exchanger. And that's also my second comment is, please, if you ask vendors to give you a quotation, ask them to mention which heat transfer coefficient that they use in their design, and what heat transfer area will they provide in their design, because then you can do your own evaluation if things are going in the right way. The third point is MVR and energy balance. This is really critical. Why is it critical? I want to explain it to you in this table format, or yeah, almost like a Sankey diagram. Don't take too much care about how big the blocks are. It's just to illustrate the concept. So if we start at the top one, and this is of course when the system would be running fine, and so we have a positive balance, the system is stable. Now, what do I mean with the system is stable? At the end, I need more energy input than that I use. Of course, at the end, it will stabilize, it will be equal, because energy cannot, let's say, disappear. But at least I need it upfront to be positive. And what do I mean is that the energy input, if you look at that, it's the energy input in the water vapor that is on the shell side condensing. So suppose that is, well, take 100 kg per hour. The second source of energy input is the energy in the evaporated injection water. Well, in fact, I get this energy because of the inefficiency of the root blower. So that's an energy input as well. The third energy input that I have is the energy input from the feed. And that, of course, is only there when the temperature of the feed is higher than the system temperature. If you combine these three, and then you get the brown arrow is the total energy input. Of course, this energy is used. It's used for compensating heat loss. At the end, the whole system is at a certain temperature, and it has the tendency to lose heat to the surroundings. So you lose heat. That's the first part of where the energy is used. And then the second part, which is of course what we're looking for, is we want to evaporate water. So it's the energy for evaporation of this same 100 kg of water. At the end, when the left side is larger than the right side, the system can work, because this will mean that I generate a bit more vapor. And that means that at the end, the pressure will stabilize and will settle itself so that both left and right become the same. But what happens now in the case that I have too much heat loss? Well, you see that in the bottom side. You see that if I lose too much heat from the system, then at the end, if I take the same energy that is needed to evaporate 100 kg of water, at the end, my energy use is more than what I put in. And this cannot be possible. So what at the end will happen is that I evaporate less than 100 kg of water. But if I evaporate less than 100 kg, also I get less energy input on the left side, and that means that you get a cascade down, and that means the system collapses, evaporation at the end will stop. So this is because too much heat loss. There is also a second reason why the same can happen. That is because the preheater might not function. Because as you see at the top, normally I get energy from the preheater, but if I have a preheater that is too much fouled or is not functioning as it should, and my feed temperature is lower than the system temperature, then also I need energy to get this feedback back to system temperature before evaporation can occur. So on the left side, I lose an energy input, and on the right side, I get an additional energy loss or an energy use. And that could lead to the same system instability. So meaning that I have a negative balance and the system can collapse, evaporation will stop. And if that happens, then of course you can have a look how to solve that. You can use additional steam, but that's of course not what you want if you look at how the core of this system should work with. So this was the third item that I wanted to illustrate in how to design and select and look upon Mvr units. So currently what we're doing together with Shachi is we have developed a standard package, an Mvr unit with self-cleaning. And for the smaller units, it's based on the roots blower. It's containerized, so it will consist of a skid with a containerized unit that contains the tanks and the circulation pumps. We have standardized capacities. Of course, they will fluctuate a bit based on, let's say, concentration ratios that you want to achieve. But we try to have a standardized unit so that also we can go to a more low-cost unit. And the only required utilities as there are would be electricity and fresh water. To end this webinar, at least the part where I explain the things, I want to come to some conclusions. If you look from the system perspective, evaporators with an Mvr, well, they provide an energy efficient solution for the treatment of wastewater. But, that's the side comment, it does require a careful system design. A conclusion from the end user perspective. From the end user perspective, I would say specify the boiling point that a vendor has to use in his design, because this is crucial. And have all the vendors specify the heat transfer coefficient, the heat transfer area, and the compressor ratio that they are considering. Because then you can evaluate if the people have done a proper job. And at the end, from your perspective, the end user, you want a system that is running and not a system that has too much problems. The last conclusion is, of course, what we are very, of course, passionate about is the self-cleaning technology in combination with the above. And because with the self-cleaning technology, we can solve the issue of fouling and clogging. We can get a plant that has a constant evaporation capacity. And we can have a plant that requires less heat transfer area and pumping power than systems that have a conventional design. So at the end, there will be a very good business case if you look from the end user perspective. With this, I want to conclude my part of the webinar and well, hand it back to Suruchi and in combination with also the questions as being raised. Suruchi, shall we go to the questions? Okay, I will go to the questions that have been raised. I think some of them I already let's say have answered in the webinar because I get a question about the compressor ratios. Well, in fact, if I just click through. And you see here the compressor ratio, the typical compressor ratio named for the roots blower and also for the centrifugal compressors. So, and that ranges from 1.4 for a single stage to 2 for a double stage. And for the roots blower, let's say it has a wider variety, and just because of how this roots blower is designed. Oh, sorry. Yeah, maybe by the way, a last remark. I forgot about that, and a short announcement from our side. What we're working on is an Mvr calculator, in which you simply can fill in what feed do I have, what is the inlet concentration, outlet concentration, what temperature do I want to run the Mvr to run on, do I want a conventional heat exchanger or a self-cleaning one, and it will calculate you how much power to use, what's the energy cost, how big has the heat exchanger have to be. So you can use that just for your own understanding, or to evaluate vendors, or to have a discussion with us. But just as a courtesy from our side to assist you. I get a small remark from the side of Shachi, is that they have a problem with their internet in the plant, so they are not able to hear it anymore. But let me continue with answering the questions. A very good question is, and in fact I should have said something about this during the presentation, and that is how to start up an Mvr unit. Because yeah, if there's no evaporation, yeah, there's also no condensation, so the plant cannot start up. So there are different options that you can follow. But you could say, and that depends on where you are going to position the Mvr unit, is, oh, there is fresh steam available. So initially I run the Mvr with fresh steam till the point that I get evaporation, and then I switch over to slowly starting up my compressor. So that is, of course, let's say it a very it's a direct way to start your system, and it will also give an easy startup. The second way to start up the system is to use, and that is more easy with the roots blower, to use the roots blower as a way to heat up your air. So you just I mean, we will also include that. You generate a way in which you at first suck in air. The air will be heated by the roots blower. So at the end you create outlet temperatures of 80-90 degrees of hot air, and this hot air is entered into the shell of the heat exchanger. And with some vents, you then can release this air again, or send it back to the inlet of the blower. So in fact, you use the blower to heat up air, and the air will heat up your system. What we effectively will do, we will make a combination between this hot air heating and an electrical heater in the condensate tank. So what we do is we heat up the condensate until the condensate tank is at 90 degrees. And then we circulate this condensate over the preheater, and at the same time we circulate the liquid that is inside the Mvr unit over the same preheater, where normally the feed would run. Now this system liquid will run, and by this we slowly heat up the unit, or we keep it up to temperature, and at the end we combine it then with the blower to run on hot air. So that are in fact the three ways for the startup. There is also a question about the cost of kilowatts per cubic meter. And for this, I would need to say at the end, when this calculator is there, you can find this out. But this is a very delicate question, because it all depends on your system design. It depends on how much kilowatt, how much compressor ratio do I take compared to the heat exchanger design. And it starts with the boiling point elevation, as I've tried to let's say it elaborate on in this presentation. So really important question, but you can only answer it if you answer it for the design of a system. Let me see what other question pops in. Yeah, so in the system that I've discussed today, we talk about a forced circulation evaporator. Reason is not because I don't like a falling film. No, the only reason is that self-cleaning can only work with a forced circulation evaporator. What I do know is that with falling film, normally there are more fouling problems than with a forced circulation evaporator. So if you really expect that you will have fouling problems, then my advice would be stick to the forced circulation evaporator. And of course, yeah, we would be really happy to also offer you the self-cleaning option. Another question which I really like is till what concentration can we go? Because that's also important to mention. Is what we sometimes notice is that people focus on the energy use of the Mvr units, but later they need a lot more energy to drive the agitated thin film dryer or to go to the spray dryer. And in fact, if you can go to higher concentrations, you have less product coming from the evaporator system. It means less effluent that you need to treat in your downstream equipment. So that saves you even more energy. So going to higher concentrations is really beneficial. And because we have the self-cleaning, we're not afraid of fouling. So we can approach, let's say, at the moment that more salts will start to precipitate. And that's also what we're working now on Shachi, is that we will push the limits of concentration, such that at the end we have less product, and less product is less energy use. So till what concentrations? It will depend on the salts, but we easily think we can go up to 35–40%, and for some salts even higher, because if they are really soluble, then you could even approach higher. So there is also a question about why not go for cleaning mechanisms. I think that's a question about. Well, in fact, if you need to clean the unit, you need to take it offline. And first of all, you start with fouling, so you do have lost capacity. If you need to clean it, it will take you time, it will take you chemicals, it will take you energy, because the system has to be up to temperature. So yeah, at the end, if there's really a fouling issue and people experience it, when we get the questions every day, then there will be a business case to go to self-cleaning. Yeah, I get a question which is very specific about a certain boiling point elevation and what will be the cost. My email address is, I guess, known, or I can tell you it's vanbeek@klarenbv.com. Please tell me your configuration. I will send you a screenshot of the calculator, and which shows you the kilowatt per cubic meter. But I cannot say that. I mean, I need to calculate that first as well. Another interesting question: what is the lifetime of an Mvr installation? Well, if you would look at the lifetime of the heat exchanger bundle, we know that our system will not influence the lifetime of the bundle, so that can easily go to up to 15 years. Lifetime in effluent systems is mostly based on the materials used and the corrosive nature. So it's really important to assess how corrosive is the liquid, and which should be the optimum material to choose. In terms of the blower or the compressor, yeah, with normal maintenance, definitely they can go over 10 years. Let me know at the list of questions. Talking about what type of effluents can be treated, at this moment we would say that the normal effluents that are available in industry with different salt combinations, even going up to higher COD concentrations. Yeah, we have proved that our system is effective in those areas. So at this moment, there are not too many limits there. I think that at this moment, I've finished all the questions that have been raised. So I just give a moment to see if there's a final question popping in. And in my other screen, I will have a look at if the people from Shachi have rejoined, because I think we're reaching the end of my presentation. For people that would like this presentation, and I also already see one question of someone that would like it, please send a mail to marketing@shachiengineering.com. They will make a list of people that are interested, and they will receive a PDF copy of this presentation. I see an actual requirement of that of the unit. We will definitely, we have noted your questions, Mr. And we will definitely get back to you. No worry on this. We will assist. Okay. At this moment in time, I would like to thank the audience for joining this webinar. Please indicate to either myself or to, I will go back to that slide, sorry for the skipping. One moment, almost there. Yeah, so you see the email address here in this slide, marketing@shachiengineering.com. Please indicate to them if you're interested and would like the presentation, or you want a dedicated presentation with myself. Please let them know, and we definitely can arrange that. Okay, thank you very much for joining. And at this moment, I will enter the webinar. Since I'm not the organizer, I have to see how I can do that. Yeah, I'm going to end the webinar. Please, yeah, indicate if you have any questions or you would be interested to know more. Thank you very much. Thank you very much, Shachi, for organizing this. And also, people that are interested, please have a look at our website, klarenbv.com, because this calculator tool, which is open, will be shared. And please also indicate if you have any questions or remarks about it, because then we can further develop this as well. Thank you very much, and wishing you a very nice day. Bye-bye.